Hello guys, so in lecture 7th, so we talk about application of partial fraction decomposition in finding inverse Laplace transform of functions, and we solve one example. In this lecture we're going to solve another example on finding inverse Laplace transform by partial fraction. The example that we want to solve is finding inverse Laplace transform of following function. Fs is equal to 2s minus 4 divided by s to the power of 4 plus s to the power of 3 plus s squared plus s. So we have a fraction in numerator, we have a polynomial. In denominator, we have a polynomial. Degree of polynomial in numerator is 1, and degree of polynomial in denominator is 4. As a result, degree of numerator is less than denominator, so we can use partial fraction decomposition to find partial fractions and then find Laplace inverse of the functions. So in the last lecture we said in order to use partial fraction decomposition, the first step is factoring denominator as much as possible, as completely as possible. First step. Factor denominator as completely as possible. So in denominator we have s to the power of 4 plus s cubed plus s squared plus s. So I can factor s. As a result, we have s cubed plus s squared plus s plus 1. So we have to see if it's as completely as possible. For sure not. As a result, I try to simplify it. We have s. I factor out s squared from first two parts of the function, so s cubed and s squared. If I factor out s squared, so I have s plus 1, and I write the rest, which is s plus 1. Now we have s plus 1 in common. I can factor out s plus 1, so we have s times s plus 1. It's times, so here we have s squared times s plus 1. We have s squared here, and here we have just s plus 1. As a result, it's plus 1. So we could factor denominator, so it's equal to s times s plus 1 times s squared plus 1. It's as much as possible, as completely as possible. We cannot go further. I can write Laplace inverse of function that we have, so it's equal to Laplace inverse of 2s minus 4 divided by s to the power of 4 plus s cubed plus s squared plus s. I can write it in this form. It's equal to Laplace inverse of numerator is the same, is 2s minus 4, and denominator is s times s plus 1 times s squared plus 1. The second step in finding partial fraction is looking at the factors in denominator, and based on the factors in denominator, so we have to pick one partial fraction term from the table that we have here. For example, in this case, so we have 2s minus 4 divided by s times s plus 1 times s squared plus 1. So we have 3 factors in denominator, first one, second one, and third one. And for each factor, we can find one term in partial fraction decomposition from the table. So for the first factor, we have just s. The second one we have s plus 1. And for the third one we have s squared plus 1. For the first partial fraction, we are in the first category because we have only s. So a is equal to 1, b is equal to 0. As a result, we have a over s. For the second one, we have s plus 1. Again, we are in the first category. As a result, I have to pick another variable. So I say it's equal to b. And for the third one, we have s squared plus 1. So s squared plus 1 is in the third category. So if a is equal to 1, b is equal to 0, and c is equal to 1, so we are in the third category. As a result, we have to have a and b here, and they are already taken. So as a result, I use c and d. So we have cs plus d. So now we have to find a, b, and c and d. So what we have to do, we have to add these three terms: a over s plus b over s plus 1 plus cs plus d over s squared plus 1. So in numerator we have s times s plus 1 times s squared plus 1. In the numerator we have a times s plus 1 times s squared plus 1 plus b times s times s squared plus 1 plus cs plus d times s times s plus 1. So in these two fractions, they are equal, denominator is the same. As a result, numerator should be the same. So we can write 2s minus 4 is equal to a times s plus 1 times s squared plus 1 plus b times s times s squared plus 1 plus c s plus d times s times s plus 1. S times s plus 1. We have to find a, b, c, and d. In order to find a, b, c, and d, so in the last lecture we said we have two different solutions. At first we used the second solution because it's easier in case we end up with the result. So in the second solution, I want to use the second solution. We said if two equations are equal, left hand side is equal to right hand side, it should be equal for all the magnitudes of s. As a result, I plugged different magnitudes for s in the right and left hand side of equation. At first I plug s equal to minus 1. If I plug s equal to minus 1, in left hand side of equation we have 2 times minus 1 is minus 2, minus 4 is minus 6. In right hand side of equation, s plus 1, so s is equal to minus 1, minus 1 plus 1 is 0, a times 0, so it's gone, plus here we have b times minus 1 is minus b, minus 1 squared is 1 plus 2 plus 1 is 2, so it's minus 2b. For here we have s plus 1, so s is minus 1, minus 1 plus 1 is 0. As a result, this term is gone, so we can say that b is equal to 3. Now I assume s is equal to 0. Left hand side of the equation, 2 times 0 minus 4 is minus 4. Right hand side of the equation, 0 plus 1 is 1, 0 plus 1 is 1, so we have just a. b times 0 is 0, cs plus d times 0 is 0. As a result, a is equal to minus 4. Now we want to find C and D capital, C capital and D capital. So what I have to plug in this equation to find C and D. So if you see here in this equation, you can see that we cannot consider any value for S to find C and D directly. So because here we have S squared plus 1. So we can, S should be equal to a complex number if you want to get rid of the first term and second term. As a result, it's not doable to find C and D using the second solution. That's why in the last lecture said that this solution sometimes works. If it works, so for sure you end up with a good result. For example, I'm pretty sure that A is equal to minus 4 and B is equal to 3. But for finding C and D, I have to use this first solution. So for the first solution, I just expand right hand side of equation. So in the left hand side we have 2s minus 4. It's equal to a times s plus 1. We already found a. A is equal to minus 4 times s plus 1 times s squared plus 1 plus b. B we already found it is 3 times s squared plus 1 plus cs plus d times s plus 1. I expand right hand side of equation. In left side we have 2s minus 4. In right side of the equation we have minus 4 times s squared is s cubed plus 1 times s squared is s squared plus s plus 1. For the second term we have 3 times s cubed plus 3s, plus s. And for the last one we have cs cubed plus cs squared plus ds squared plus 1. Now I look at coefficients of s cubed in right hand side of equation and left hand side of equation. Why? Because these two equations, they are equal. As a result, coefficient of s cubed in right hand side of equation should be equal to coefficient of s cubed in left hand side of equation. So coefficient of s cubed, what's coefficient of s cubed in left hand side of equation? So it's equal to 0 because we have just 2s minus 4. What's coefficient of s cubed in right hand side of equation? Here we have minus 4 times s cubed plus 3 times s cubed plus c. As a result, we can easily find c, which is equal to 1. Now we look at coefficient of s squared in right side and left hand side of equation. So coefficient of s squared in the left hand side of equation, coefficient of s squared is 0. In right hand side of equation we have minus 4 times s squared plus, here we don't have it, plus c squared. So c plus d. So we already found c is equal to 1. As a result, d should be equal to 3. Now I plug a, b, and c and d in the partial fraction. So we have Laplace inverse of 2s minus 4 divided by s to the power of 4 plus s cubed plus s squared plus s is equal to a, which is minus 4 divided by s, plus b, which is 3 divided by s plus 1, plus cs plus d. C is 1, so we have s plus 3 over s squared plus 1. So in fact, we have to find Laplace inverse of, just erase this guy, these partial fractions. I can simplify it again, so it's equal to Laplace inverse of minus 4 1 over s plus Laplace inverse of 1 over s plus 1 plus Laplace inverse of s over s squared plus 1 plus Laplace inverse of 3 times Laplace inverse of 1 over s squared plus 1. It's equal to. So if you look at the table, you can see that Laplace transform of 1 is equal to 1 over s. As a result, Laplace inverse of 1 over s is equal to 1. So we have minus 4 plus Laplace inverse of 1 over s squared 1 over s plus 1 is e to the power of minus t, plus Laplace inverse of s over s squared plus 1 is cosine t, plus Laplace inverse of 1 over s squared plus 1 is sine t. So we already have 3, so it's 3 sine t. Oh, the only mistake that I made here, we have 3 over s squared, so I have to consider 3 here. As a result, here is 3. So Laplace inverse of function is equal to minus 4 plus 3 times e to the power of minus t plus cosine t plus 3 sine